Dippy, I started recording.
Okay, great. Yeah, so hi everyone, this is Dippy here. So before moving on with today's session, I want to kind of set the expectations right. So this topic recursion, right? I think one of you on the group, I believe Aditya, he suggested a list of, subtopics that we can cover as a part of recursion. And we can see that the kind of the application space is pretty broad. If you look in terms of data structures, right? Recursion, we see the solutions around linear structures, arrays or strings, trees, graphs, and even in terms of techniques, be it dynamic programming or backtracking, divide and conquer. So the application space is pretty wide. What I thought of doing was take it as a two-part, session. So today will be very basic. For some of you who are attending, regular daily lead code sessions, solving problems using recursion, I would like to mention that this would be fairly basic, but for me, the motivation for this first part comes in because if I see a recursive code, I can understand that code for the most part, except a few algorithms, which may need a little bit more time. But for the most part, I can understand the code written by someone. But when it comes to, writing, given a problem, implement recursive code, especially in an interview, I think it becomes a little tricky. It comes with practice, but also the thought process helps. And that's one of the things I want to focus on in today's talk. So we are going to given very simple problems. You can possibly, if you have been practicing coding, you can just write it down in like 5 minutes. But that's not the agenda for today's talk. It's not about quickly writing the code. It's about pausing and thinking about the methodology so that you can, given a new problem, you can kind of have some clarity on how to start. So that's point number one. The second is in the list, there was this topic about tail recursion, which I didn't had in mind. So I'm glad it was mentioned. So I'll talk about tail recursion. Sorry, somebody saying. Okay, so I was just saying that I'll cover tail recursion and what's the idea behind it and what's the value we get from it. And the third is in preparation for the next session, I'll also show some examples of backtracking, like how in the code we spot backtracking or how to implement backtracking concept. So those are the three main highlights. With that being said, let me start with the first one here, which is about given any problem, we'll start with a simple one. How do you think about a recursive function? What are the parameters you need for that and all of that stuff? So what we can do is a problem as simple as it's like a hello world for recursive programs. Given an array, you want to print the sum of its elements, right? Using recursion. So would somebody like to volunteer and quickly write the code for it? Anybody who can give it a shot?
I can, but yeah. Is there a place where I can write, or should I share my screen?
Yeah, you can share your screen, maybe whiteboard, and yeah. So somebody's asking what's the question. The question is that you're just given an array of integers. Think of all positive integers, and you just have to compute the sum of its elements using recursion. As simple as that. Yeah, we can see your screen. And maybe you can take the function signatures as, yeah, returning integer, get sum, and you're passing an array.
Okay. Can you? Sorry. I'll be writing.
Just an integer array, yeah. It's fine.
Yeah. Okay. I'll be writing in. I thought I'll write in JavaScript, but I'll just say this is int array.
Yeah. Okay.
So the way I'm thinking is in order to call it recursively. So what I can do is my limiting condition. First, when I write any recursive function, I think about the limiting condition. The
Right.
limiting condition is if I'm handling the index which do not belong to the array, then I should return 0. Otherwise, that value. So I'm just thinking probably I will start from the.
I think there was a one request on the share about, can you zoom your screen?
Oh yes, sure. How do I do it?
Yeah. Okay, great. Thanks.
So the idea that I'm thinking is basically what is an array?
You can take some elements like any, yeah.
Okay. So the idea is that this has length 4. So I will start with the right end.
Okay.
And I will say I'll first call whatever the sum of this plus 4. I will return that. Similarly, when I'm handling it, I will basically say, okay, give me the sum of this, then plus 3.
3 to it.
Yeah. So I will say array and the index that I'm handling, idx, which will be array length -1, because that is how it will be. Okay, so with that, so if my index is less than 0, then return 0.
Okay.
And then otherwise, basically return whatever is at the current index. So I'm basically doing the 4 part here.
Right.
Plus, again, this is the smaller problem. So I will just use the same function name here. I'll say get sum array, and my index is index -1. So that's all.
Yeah. So essentially, you're starting from the end, and you're just going backwards, and you're just stopping. Once you're done with your array, you return 0, and that's it. So yeah, that's great. So this was, so if we kind of try to dissect this, given that this problem is so simple and we have solved so many, like much more complex problems. So this might seem like obvious and quick, but to understand the process, what you essentially did here was you tried to, given a function get sum, when you were thinking about this, you were actually trying to understand what variables do you need in your recursive call. Like you started from the end, so you need the index. That's why you passed the array.length -1. And then you also had some sense of how you are going to, divide your problems, how you are going to make it smaller by passing index -1 in every recursive call, right? So this is essentially how I tend to think about it anytime I have to write a recursive function. And in preparation for this talk, I was trying to solve few questions. And it so happened that I came up with a little different approaches to writing these algorithms from what was given in the online tutorials. So this is great. Now with that being there, I want to show two other implementations I did about the same problem, right? So let me share my screen. Let me know when you all can see it.
Yeah, I can see.
Okay, so I'm not sure who was who volunteered. Was it
Rajendra.
Rajendra? Okay, so Rajendra, you went with this approach too, right? Where you are starting from the end and you are decrementing the index at every step. And this is just a little different. I stopped at first element. You let it, you traverse the whole array. But this is the approach you followed. But it really depends on how you're thinking about the problem. This was totally fine, but I just want to show examples of, depending on at the time of the interview, how you approach the problem, there can be different ways, right? In the first case, I thought, okay, I'm going to start from the beginning and I'm going to stop at the end. Now, when I say that concept, I need a way to track where my end, when I have reached the last element. That's why I need my current index and the index of the last element. I mean, these are pretty straightforward, but the gist is that I personally don't go with one approach. I don't tend to look at, the solutions and try to keep that in mind. But the natural way of thinking is, what are the elements that you need to process your recursive call? And if they are changing, then how are you going to change them? So in the first approach here, I am going from the beginning till the end. So I am incrementing my index. And in the second approach, I'm other way.
Sorry to interrupt. I have one question.
Yeah.
In the first approach, I hope most of the language will give option to find the length, right? Do we really need to pass the n? Can't we use the array length?
Yeah, we can actually. That's a good point. We don't really need to pass the end variable. We can use the array.length. Sure. Yeah. Good point.
It's depend on the again language. So let's go with this implementation. Like C++
Okay.
doesn't have that. Okay.
Oh,
so
okay.
Okay.
yeah.
Okay. Good to know. Yeah. But just as in the languages which have it, sure, that's totally fine. And the kind of advantage I see there is, with each recursive call, you create the stack frames, right? So if we can reduce the data that is being passed, I think that should be, anyways, helpful. So that's fine.
Thanks.
So in the second approach, I was saying that once we know what values do we need to process our recursive call, we also need to keep in mind how we are going to call the recursive function. Here I'm going backwards, here I'm going forward. The third approach I tried was keeping track of the remaining elements. So if I have 4 elements in my list, my logic was, if I have only 1 element remaining, I just return that. Otherwise, I just keep adding to the sum. So that was another idea.
So third approach is basically the length of the array only.
Yeah. It is length of the array, but yeah, that's true. You can think of it that way. Yeah, I'm passing the full length and then decrementing. Yeah. So fairly basic, but just to highlight the concept here. Yeah, this is what I just iterated here. I mean, recursion is one topic where I feel that the more we practice on our own, the better we get. You can teach a concept, but it's like more about practice. So this was the second example I took, count number of occurrences of character in a given string. So this one first is how I thought about it. I didn't even come to this solution below, which was given in one of the online links. And I would like suggestion from everyone here, but my personal take is, in an interview, if I'm writing a recursive code, I don't want to suddenly get into this clean, best optimal code. I want to write a functional recursive code which makes sense and then maybe improve on it. But if I tend to go on a very clean code, like I believe the one below is much shorter and cleaner than what I have, but I tend to personally get confused, or I find it much easier and intuitive to first just follow my own methodology rather than optimize solution. So here, one other thing that I want to mention is in this examples here, you notice I have always used this helper function. So if I'm passing additional elements to for my recursive call, then whatever function is given to me, I'm not going to change that because that's more like the interface to the user, but I tend to create a helper method where I customize it. So function like this, right? Count number of occurrences of character in a given string. So I'm given this variable test and I want to count how many times t occurs. I think somebody raised a hand.
Yeah, so actually, I have some questions to ask. So first thing is, if we see a question, so for example, this count the number of occurrences
Yeah,
characters. So seeing this question first, what we'll think, we'll first figure out the logic, and we will maybe we can move on to the iterative solution or else a recursive solution. Might be if we already know this recursive solution, we will apply it. Most of the people will apply the iterative solution only. So because we have a lot of disadvantages of using a recursive solution because it consumes a lot stack frame. I wanted to know that if we see a problem, when will we like think of a recursive solution for
yeah,
this
my
particular?
personal, yeah, one of the things I can think of there is some problems. For example, this one. This can be very much first thought comes as iterative, maybe. But there are some problems like trees related where your natural thinking process is also recursive. That I'm going to traverse this and that. So I think that is one hint where you might go naturally with recursion. The other
So
thing
basically,
is,
if we take a tree, obviously we are going depth-wise in interior of the nodes. So okay, we are taking the recursive approach. That's fine,
right,
and backtracking also.
yeah,
For some questions also, I have seen they have used recursion instead of
right,
iterative.
right.
So
So
how should
some
we
things are very amenable, like
the
some things are
problem
very
down?
natural.
And
Yeah, sorry, go ahead.
so like if we see a problem, like how do we like break down to recursive
I
function that is for
personally, I won't jump to, recursion just for the unless interviewer typically, he points me to that. Can you write a recursive version of it? If given a problem, I first can think of only iterative one. If it seems natural, I think I'll talk about that one. But having said that, you also need to think through, maybe as long as you can reason about why you choose one over the other and the complexity analysis, right? That can be another indicator. But I won't directly jump to recursive if, for a problem like this, it's just that we are covering this topic. So I want to show some examples, but it really depends on the nature of the problem that in the interview, how I will solve it. Um, yeah, that would be my thing. But if I,
and one more thing, like if we see a problem, like how to arrive with a recursive formula. Okay, I know it's based on the practice, but can you like give some questions so that we can fix a formula?
yeah, so what I have done is, as I was doing problems on my own, I have listed 2 or 3 additional problems here, which I have solved recursively.
Okay.
But I didn't want to just show the code because I don't know how useful that would be. But if you're interested, we can talk about that, offline. I can, you can try it. I can share my code. So that's one way. Um, and one other thing I have observed in while writing recursive code is you really need to be very comfortable with the data structure. So sometimes when you're trying to solve a graph problem, even though you understand depth first search, but the moment you start writing the code, if you're not comfortable with, these graph general, like how you'll represent graph or some basic functions, it can be confusing during the interview. So having bit grasp on like matrices, right? That is another thing, representing a grid, maze type of problems. If you're not very comfortable with uh, the graph, the data structure representation, or the simple methods, I think it's a kind of a tricky, situation. Um, and I'm saying again about interview because that's more like a time boxed situation, right? You don't want to get confused in these details. You want to focus on the algorithm. So
Okay.
these were some of my thoughts, but yeah.
So I have seen, for example, Abdul Bari's videos of time complexity of recursive programs.
Yeah.
I would tell you to, I want to add something because he have taken some basic standard recursive algorithms, and he have listed out the formula of means like a function formula, like if n is greater than 0, and we'll have this, we have 1. So if n is I mean, if n is less than 0, then if we will arrive at 1. If n is greater than 0, then we will have a function like t of n minus 1 plus something else.
Recurrence
So,
relations. Yeah.
yeah, recurrence relation, yeah. So based on that, we find the time complexity.
Mm-hmm.
So likewise, for a larger like DFS and graph problem, like how do we come up with that
Yeah,
recurrence?
so recurrence relation is definitely, I believe it's more of a, mathematical and theoretical idea. That is
So
how
we
the
need that maybe
complexities
to
are
find
done.
the time complexity for bigger problems. Do we need to arrive that in a interview wise?
I don't think so. I think those are the foundations, right? But if you understand the foundations well, then you can just apply them. You don't need to write recurrence relation and stuff like that during the interview. I take them more as a foundation. I don't take them as that. You don't need a derivation during the interview, right? As long as you capture the concept from that recurrence relation, it should be fine. As a
Okay.
very simple example, in binary search, right, when you're
Mm.
writing cursive code, you're splitting your array each time in half. And if you go back to its recurrence relation, essentially you'll come up with this logarithmic stuff, right? Why do we have log n to the base 2? Because each time we are dividing the array in two parts. Whereas if you start doing ternary search, right, you divide your array in three parts. Then you will just write your complexity as log n base 3. So if you have understanding of these concepts and all of this, what I'm saying is coming essentially from a recurrence relation. But if you just capture the gist of it, then I think for interview that should be fine.
Okay, ma'am. Thank you so much.
Yeah. I mean, anyone else has any thoughts on what was asked? Please feel free to jump in.
Yeah, go ahead.
Okay.
Dippy, do you mind increasing the screen?
Oh yeah,
And
yeah.
if not font, then document someone. Yeah. Okay.
Yeah. Um,
So if so, can I add one thing to how what if there is a template for designing recursive solutions? I think that was the question asked.
um, yeah, sure. You want to add to that?
No, please ignore. I don't want to hurt the flow. Maybe we can discuss later.
Um, okay. Either way, I mean, I think it's fine if we are having this discussion. If you have some thoughts.
Okay, so I generally, so I have got a template for designing recursive problems. So
Okay.
what I usually do is, can I share my screen?
Sure.
How to share my screen?
Maybe I can stop sharing and.
Yes, yes. Thank you. Okay. Yeah. Can everyone see my screen?
Yeah.
So first of all, the first thing is uh, coming up with a function signature.
Yeah.
So that is a challenge in designing any recursive problem.
Right.
First thing I usually decide is my problem, is my function going to return something to its parent? So that is first thing. So if it doesn't, then of course it is void. And then just for the fun of it, let us say it is func1. And then I need to take at least one parameter, because if I'm not taking any parameter, then I cannot basically have a subset of the problem. So my parameter should be representing the problem itself. In that sense, suppose I'm taking a tree. Then in the recursive invocation of the function, I'll be basically invoking the function with subset of this tree, a subtree of this tree. So at least there will be one parameter, and then other parameters will follow as I need it. So for example, the function that we saw in the morning, so I had to take length as another parameter, because using that I was getting my shorter sub problem. So anything that is required to come to a shorter sub problem, I will take that as a parameter. So after that, very briefly I will touch. The first thing I do is I write my limiting conditions. In the limiting conditions sections, there are two types of limiting conditions. One were I would negative limiting, in the sense that the negative limiting's role is to basically define the problem. So for example, in the last one, I probably wrote, where is the last one?
So you wrote like if index is less than 0.
Yes. Because I know if index cannot be less than 0 for a valid, that was my array.
Yeah.
So that was the negative, basically limiting condition. I basically took out that all the negative indices from my consideration. I just threw that away. So then there will come positive limiting or positive limiting. So your sample where you said if index equals to 0, then return
the array value at that index. Yeah.
Array value. That is an example of a positive limiting. Whatever. So basically, first comes limiting condition. After that, I very kind of so this is a must. Limiting condition is a must. Without that, there cannot be any recursive function. Now we are coming to the meat of the function. The meat of the function is kind of there is a standard to it. So let me think about the problem a little bit in this two ways. One way is, let us take an example of, say, I'm printing a tree. If I'm printing a directory tree. If I'm printing a directory tree, unless I print the root, then I cannot print its leaves, in the sense that, or say I'm creating a tree. Unless I create the root node, I cannot, where would the children sit?
Right.
So that's where, that is the pre-order. Basically, I do my work before I delegate to my children. So I will just say pre-order. That is one way. Basically, I do my work first.
Right.
And then recursively invoke my children. Then the other one is basically post order. One example is, so any problem where it treats you like a manager. For example, can you print the total size a directory takes, including its subdirectory and files? That is when, unless I get the numbers, get the size of my subdirectories, I cannot report that up to my parent. So when there is such a thing that I need to report on behalf of my children, that is where I basically do my work after I get the work from my children.
Yeah.
So I do recursive call for my children. So I add one. Usually it is left, right, or this can be extended to if I extend it, that becomes DFS, depth first traversal. First I do recursive call and I get all the values. Then I just add my value.
Mm.
My value is not a recursive call here.
Yeah.
And then I just return that.
Mm.
So once it is, so it is very easy to verify to which category the problem belongs to. Either I need to do the work first before I call the children, or I recursively call the children first. Otherwise, I cannot report the totality to the parent, to whoever
Yeah.
told me. If so, one is pre-order, the other is post-order. Obviously, if the problem doesn't fit to any of them, it must be in order.
Mm.
So with this template, I found most of the problems can be solved.
No, this is really neat and very clear. Thanks for sharing. I think I really liked it. Pre-order and post-order, and because this is also a confusion point while writing the code, that whether I need to do this value recursive call first or at the later point. So thanks a lot.
I have
Any
one
questions?
question on the set line, point 2. So value plus recursive or recursive plus value going to make a difference here?
What do you mean by difference?
I mean, the post order means, if I understood correctly, you are saying we have to call the recursive first and then add the value.
Oh, that doesn't, no, it is the same thing.
Okay.
If you mean this, that is also fine. All I'm saying is, so
Okay.
basically, what I'm saying is, I first, so it is a simple statement where both of them are kind of, this is just an addition operation which is commutative.
Okay.
But usually it means you might have to do the recursive call first, then you go and get your value.
Oh, okay. Yeah, thanks. I got it. We are trying to process something on the result of the sub problem.
Exactly.
Okay.
Yes.
Thank you.
So Rajendra, on that note, I was thinking of it a little differently, but I'm glad we have having this discussion. So, for example, if I'm printing, like post-order traversal, right? In your example, where you were adding the value, given that it's commutative, it doesn't matter. But if, let's say, printing the tree in a certain order, right? Then when I do I have to do my recursive call for the left node first, and then print the value, and then do the other recursive call. So the order there, I think depending on the operation, the order will matter, right?
That's correct. That's correct.
If I'm just doing the sum of nodes of my, tree, then value plus recursive or recursive plus value, same thing.
That was a bad example. Please don't understood.
No. I'm just saying for my own understanding. I'm not trying to point to your thing.
No. What I'm saying is, what point I was making was not clear. So that was a bad example. Whoever basically asked for the clarification. Plus, it's not a, so what I was saying is the order of computation, where the recursive call for the sub problem with respect to the real work, the real work, which is non-recursive anyway. Because recursion is not a magic. Only a part of it is recursive always, and the other part has to contribute solid values, non-recursive values.
Correct.
So I was basically arranging the order. I was just giving a yardstick how to basically shape the thought process. So yes, what you said, the printing, I mean, I think there should not be any doubt there.
Yeah.
If there is any doubt, I can again go over it.
No, it makes sense to me.
Okay.
And one more thing is, maybe your main intention is to say the process, I believe. Maybe you can say pre-process, post-process, maybe. The pre-order, post-order is a little bit confusing with the tree pre-order, post-order thing.
Okay, that is also, yeah, I'm basically thinking about the order of
Yeah.
computation order, I would say.
Thanks for clarifying. Yeah.
This is really clear and concise. So thanks.
Thank you. I'll stop the sharing.
Yeah. So getting back here. All right. So I think from that perspective, I think we can follow that thought process now, looking at this example. So I'm just counting, given a string, counting how many times a certain character occurs. So what I did was I was given this function signature on line 10, but for when I started writing recursion, thinking of what kind of parameters I would need, I wrote a helper function, and that's where I passed additional parameters. And this would be line 17, 18 is, I'm just saying that when I reach the end of the string, that's when I return 0, move past the complete string, then I return 0. And this becomes my, like the base condition, limiting condition. And then here I am, yeah, I mean, this is more like going character by character. And if the character matches, then add 1, otherwise not. Pretty straightforward there. But the implementation I saw online was something like this, where they were, rather than trying to pass additional parameters, they were trying to create a copy of the string and mutate the string, and so this was a simpler, that way cleaner implementation without additional parameters.
But memory wise, it may be bad, right?
Yeah, because every time a new instance of string is created. Yeah. True. So I think, overall, if we can, articulate these trade-offs, like you just said, I think it helps in the interview rather than just solving the problem. Okay. So this I highlighted about having a helper function, right? So you don't necessarily need to just confine yourself that given this function, I just have to work on this. Now, the next thing I wanted to talk about was this idea of, I want to introduce the idea of tail recursion here. So if you see the general recursion, we all know that it's based on this concept of having these stack frames. And here I'm showing an example for this getSum function, where I started with the bottommost call here. So I'm passing the current index is 0, and the end is my length of the array. So the example I'm taking is this 4-element array. So what we notice is, based on my implementation, in every stack frame, I am doing this. I'm passing the array value at the current index, and then I'm placing a recursive call, right? So each stack frame is essentially calling another function, but it's also preserving that whatever result it gets from that function, it has to add something to it, right? So this is how a stack trace looks like for this implementation. And this is one of the cost factors of recursion, that sometimes, if your stack goes too deep, that is the overhead. What tail recursion does is it allows you to, I would say, either eliminate in some cases or reduce this stack space used. So let me take an example of this function only. These are some interpretations I found on web of how people tend to think about it. So a recursive call is tail recursive if its result is not involved in any further processing. So in this example here, when I was showing the previous one, so the result of this call, right, further needs to be added to another value. So it's not complete. This function call is not complete just if I get the result of this subcall, right? I further need to add it to my whatever value I have in that stack frame. So this function is not tail recursive from that perspective. So what is what would be a tail recursive implementation of this is,
So the tail is not a stopping condition.
starting condition as in?
No, sorry. I thought like when you are showing this content, I thought tail is like a stopping condition. Is that not?
No,
Oh,
it's
okay.
not a stopping condition, but I'm trying to see how this thing is. Is it clear, this size for?
Maybe you can increase little bit.
Yeah.
Yeah, I think it's okay.
Okay. So tail recursion is saying that in a given stack frame, all you need to return value from this is the result of your recursive call. That's all. You're not maintaining any additional, when it comes back to the stack frame, it doesn't need to do any additional computation. So in the previous,
Okay.
I was adding, that array index, current array value. But in this case, what I'm doing is I'm maintaining the sum as an additional variable in my recursive call, right? So we'll see how that affects the stack frame. But the idea is that, for example, this rephrasing one is nicer one. So it says that the caller does not need to wait for the result due to any more things that have to be done with it. So in this case, as soon as I return this call, I have my sum in the variable. I don't need to do anything else. Make sense?
Okay.
So the way I would call this function is current index is 0 in the beginning. Elements remaining is, let's say if I have an array with 4 elements, then I would say 4 and sum is 0, right? So in this recursive call, once I complete my array, I have my sum ready with me. I don't need to go back to the, other stacks and do any additional computation. So that's the idea of it. And the way to accomplish this tail recursion is to use this accumulator, a variable
So
in your.
finally, in the stack, you will have that some answer, and you
Yes,
will pop it out, or
yes. So this is how I'm showing in this walkthrough. So what is the benefit you get by tail recursion, right? In the general recursion, you're building a stack. So if you have, I was showing previously, you had 4 stack frames, but because of tail recursion, compiler is able to judge that I don't need to do any additional computation. This is a tail recursion. So it doesn't create additional stack frames. It reuses them. So when you start here, right, this is my first call. So rather than creating another frame on top of it, it just reuses this same frame. It kind of overwrites this and it gives you this value. And at the end, when you hit the condition that you're done with your array traversal, you have your sum right away, 26. Does everybody see the benefit of this idea? So you're not incurring any stack overhead in this example. We'll see others where it's not that you're not incurring stack overhead, but it's reduced. But in this example, you are not maintaining really the stack frames. You're just reusing them. Does everybody like any questions on this? Or?
Sorry, I couldn't follow like what you
Yeah.
mean by follow.
Yeah. So if you see the previous example, right, where I wasn't using tail recursion, right? Every time I get the result from my sub call, I need to take that value and I need to add my what
Yes.
value I had so far.
Yeah.
So here I'm showing when I started from this call, and this is my array. So I took 2 and I have to add the rest.
Yes.
So this means that I can, when I place a call to this function, I create another stack frame, right?
Yes. Yes.
So this is how basic recursion works.
Yes.
The reason you are maintaining these stacks is because these values, right, are different in each stack.
Yes. Yes.
But in tail recursion, what it does is it says, I don't need to keep track of these additional, work that I need to do. I am just going to add this data to my function call. So if I just add it here, then I'm not doing anything here, right?
Okay.
Right? And in that case, when I place a call to this function, do I really need to create another stack frame? I can just overwrite it. Right? So if I say 2, I can say 2, 6, 8. And at the top, right, I'll have the sum.
Oh,
And I
okay.
can just return the sum. I don't need to create this pile here. I can just keep reusing it.
Okay, but still you will be having the same number of recursive call as well as the memory also will be same, right? I couldn't.
No, so if you see the number of calls, the time will be the same because recursive
Okay.
calls will be the same, but the space, right? Now you're in this case, you have like 4 stack frames. But in
Yes.
case of tail recursion, you're just using 1 stack frame. So your memory usage is reduced.
Okay.
Right? Like you usually get sometimes in larger problems, you run into stack overflow.
Yes.
Right? Which is why like you're exhausting the space available to you. But in case of tail recursion, if you can implement that in a given problem, essentially you're just having one, stack frame.
Your idea looks very interesting, but I couldn't really get the real. If whatever you are explaining is really possible, that is very interesting. But even can you come down with your tail recursive example flow? So here also you okay. 1, 2, 3, 4, 5 calls, right? Here also we are making 5 calls. I mean 5 times the
Yes.
recursive. Okay.
Yes. So number of calls is same. You're not reducing your number of recursive calls. So if you think of recursion, there are 2 parts to it. One is number of times you're calling the function, which is your time complexity.
Yeah.
But the other part is the space overhead, right? Which is the major, because of the stacks, you're adding the space in recursion, right? The more stack goes deep, like in depth first search versus breadth first search, right?
Yeah.
That is one of the points we make. In depth first search, you're going really deep, so your stack is growing.
Yes, actually that stack overflow is based on the depth of the stack, right? Because even here also we are calling 5 times. It means it's going a depth of 5, right? How
No,
it
no, no,
will...
no. So in this case, even though, so that's why I'm trying to isolate those 2 concepts. So even though you're calling 5 times, but stack depth is not 5. Your stack depth is 1 in this example, because you are every time replacing your stack frame with new values. So your number of, you can think of it as number, your, like if I put this in layer fashion, all I'm saying is that I start with this. In general recursion, I will put this call on top of it, right?
Yes, yes.
But in tail recursion, especially in this example, and we'll see something else also, but in this example, I'm saying I'm not creating a new stack frame. I am just overriding my same stack frame with this new values, because I don't need anything from this.
Okay, maybe then are you saying all the input parameter going to be an object, and the same object you will be updating again and again?
Yes, yes.
Can I quickly put one comment?
Yeah,
so probably another way to understand is that when suppose your return value is used in your function, right? Then compiler need to keep track of all the return values separately. So function will call function, same function it is calling, right? Yeah. So function, the first call need the value from the second call, and second call need the value from the third call. Then they compiler or language need to create a stack.
Yeah.
Your first call also returning the value. I mean, everybody is returning the value, but the value, whatever you are returning, is not depend on. So whatever the first call return the value is not depend on this, other recursive function. So in that case, basically there is no need to maintain the chapter stack. and that's why compiler do the optimization and saying that I'm gonna reuse that memory. And
Nice.
and basically why we Stack Overflow is nothing but each language has a predefined memory to put this kind of build this kind of structure. Now if we are just keep reusing memory, then we will never run out of it. So we can go we can have a much more longer recursive call.
Oh, nice. Thank you so much, Deepthi and Bhavesh. This was something new. I learned completely new. Thank you.
Thanks. And if you actually think about where this idea came from is, if you go back to your original recursion, and if you follow the same methodology that you keep creating stack frames, right? Even with this approach, then essentially based on this code, what you're saying is every time a recursive call is finished, you're just popping that frame from the stack, right? You're not doing anything else. So that's where I think compiler optimization comes in, that it detects that this is the pattern and it doesn't need to really create a stack frame.
Okay, nice. Thank you.
And I haven't really used it like in any general problem, but this was an interesting concept, and I was reading about it that I think in functional programming languages this is there, but I'm not sure if it's supported in in general or all programming languages. But the concept is interesting. And we'll see in, so this was an example where we could totally avoid creating these stacks. But you will see other examples, for example, tree traversals or quick sort is an example where you are, if you think about the basic algorithm, you are actually creating a pivot element and then you are doing quick sort on half of the array, one part of the array, and you're placing another recursive call on another part of the array. So I don't have the example today because I plan to cover it. It's a little more elaborate. So I plan to cover it next time, but the intuition is that there you are making two recursive calls, one for the left part of the array, one for the right. So you can actually reduce that using tail recursion. So the takeaway there is you shouldn't think of tail recursion as a way to completely eliminate, your stacks space. You can reduce it or to, like minimal. Yeah, that's the essence of tail recursion.
So there is a question on lead code. I think linked list reverse nodes in K groups. That is one example of tail recursion.
Okay,
So how I understood tail recursion is you do the computation first and then you make a recursive call. Then you don't need to wait about the results because you're already done with your results. So basically the computation is done first and then a recursive call. Like I think you have mentioned. That's how I understood tail recursion.
Yeah, that's true. So Asim, even when we do the computation before, for example, this something, I think would it be right to say that it has to be passed to your function, like there has to be some accumulator, right? Because otherwise you would need to come back to the stack.
Yes.
Right. If there is some operation that you need to combine with your recursive call, like the way I was doing previously, I was adding the array value, then that's not tail recursion. But if if I'm just printing a value, then Asim, as you're saying, I can just print the value, do this, that's fine. Depends on the nature of the operation.
Once the call stack will come back, it has nothing to do here. It will just go back to parent,
Right,
and
right.
Because you already did your computation, the sum plus array current index.
I think that's where this second way, this is pretty often what I see online. A recursive call is tail recursive when it's the last thing the caller does. But it wasn't intuitive to me until I went through other.
So basically, in tail recursion, we need to have the computation inside the recursive call. That is the that is the meaning, I guess.
Well,
I think that's correct.
Yeah.
One quick way to look at is, suppose I am returning, right? I am returning, let's say that return current value plus my recursive call. That means I need to have a return value from each function, each call separately. Now it doesn't mean that we have to pass it, but I can have in else in this example, right? I can calculate the value and then that basically pass it. Yes, I mean we have to pass that.
Yeah, we have to pass it. Right?
So we won't have the accumulator separately. So I mean, that is what we are actually avoiding
Yeah,
the
we
tail
should
recursion.
pass the accumulator with the recursive function so that we can just.
I think the basic thumb rule is don't try to do any operation on the return value of the subproblem.
Yes, exactly.
Yeah, I mean, if you can reduce that, right? For example, if you are finding the height of the tree, you might not be able to do it because you have to return one of the two value.
Yeah.
Either left or right side. So whatever you do, you can't do that. So in that case, you can't use that. But yes, if you can reduce a problem so that you don't use the return value, and still it is a recursive call, then there will be advantage of the recursive.
Definitely, like when we do the second part, taking more examples around trees, because as Bhavesh is pointing, right, you may not be able to completely eliminate it, but because in tree traversal, you have to handle the duplication factor and the subtrees. But yeah, like one of the ideas is accumulator. We'll see more.
Dippy, there is one comment from Rajesh. I'm not sure what he was trying to say.
Oh, I can't see the comments while sharing.
Okay, we can take an example on. Rajesh, you want to elaborate on your comment, please?
Yeah, so definitely. So I have one question saying like just now I gave one interview where they have asked me the same thing. So I resolved the first case saying like where we have a string with the AAA, BB and CC, where we have to return the string value as A3, B2 and C2.
Okay.
It's the count value of the each character. Okay, but now the second thing it came like my algorithm failed. I'm like the code failed for the second example because I was trying with the same thing. So I mean like I tried with the normal for loop and calculating those things, but they asked me later. They asked me like, can we use the recursion? So when I'm like when you are explaining this thing, so I was just articulating this thing like whether we can go ahead with the recursion for these two solutions.
Oh, I see. Okay. All right. Maybe we can take it later. Yes.
Yeah, we have to just
looks
think
like
through. Thanks for sharing.
Definitely.
Yeah. And the question and the pointer that Asim gave is also very helpful. I would say I can take a note of it and share after that. We should try to look for solve problem if it's tail recursive, and that would be good practice.
Yeah.
And this is
Sorry, I have one question. I couldn't get the previous thing, the Rajesh thing. So is it not implementable in recursive? Is that what you?
No, he's just sharing the question.
Oh, okay, sure.
And he's saying that we are on that same topic, so he just shared the question.
Oh, okay, sure. Thank you.
Yeah.
So the other thing I was mentioning is I was just trying different problems. So I tried these two problems. Again, very simple, trivial ones, but coming to the point of how we define function signature and stuff. So if anyone later wants to try this, and we can share how we thought about it. So this is not taking this right now because just showing the solution won't help. So that was about that concept of defining function signature. Next, I wanted to quickly talk about backtracking. Just this is more of an introduction. We'll go deeper next time. But the way I was thinking about this is depth first search, right? We are we can think about it in terms of recursion, but how do I spot in a code, like if I were to think about backtracking, what is it in the code? How would I implement it? That was first question on my mind. And the second thing is looking at some existing code and spotting how they are implementing backtracking. What is that section in the code which tells me this is how they are backtracking? So this is where I am in my analysis. So I wanted to kind of quickly share that. I have two examples. I can start with this. So pretty standard depth first search. So we understand the idea that we start from, if we are given a depth first search for a tree, then you're starting from the root and you're going all the way to one branch. And when you're hitting the last node, leaf node in that branch, you are essentially backtracking. So the question to me was, okay, how do I spot backtracking? So does anyone wants to kind of explain how, where is that pattern in the code which is kind of referring to backtracking here?
The if condition, not visited.
If not visited, would that be backtracking? This is more of a discussion. I am interpreting it a little differently, but
DF is recursive is backtracking.
Yeah. I mean, we know by algorithm it is backtracking, right? If I'm doing this simple tree, that we understand the concept, but I was trying to more focus on from the code level. If I were to write a code, then how do I capture this concept of backtracking? Maybe I can start with my interpretation and then we can build on what others. So my thinking is that essentially backtracking is you get to a point from where you don't have any further, path to traverse, right? Or anything to do there. And that time you have, and that's not your solution. So that time you have to kind of go back to your previous solution. You have to ignore that point and you have to go back to your previous solution. So in this case, I'm looking at it as that when I'm doing this recursive call, eventually I will get to this point where if I have, let's say, so once I get to, I start from 7, I'm getting, I mark these are the operations I have to do in general in every node traversal. And then when I look at its neighbors, I go to, it's not visited, 6 is not visited. And then I place another recursive call. So when I get to 2, right, I place this recursive call. I do these operations. At this point, I do not have any of its neighbors. So to me, this is like the point where I just stop doing any further operation and then I go back to my previous one. This was one of the kind of the patterns I observed, that backtracking is essentially about when you hit a space where you don't have anything else to do and you just stop there, which is what I did here. I didn't go in this loop. And then I picked my, it's essentially like in recursion, I pop the stack frame and then I go back to my other previous solution. I don't know how, like, maybe this is just like I was going a little too deep in the interpretation of or how people look at that. I have another example of N Queen's problem, which is another way of looking at backtracking. Maybe we can take that up and then that will help more. Yeah, so this is a typical N queens, right? So you have to place N queens on a board, N by N board, so that no two queens attack each other. By attacking, you mean that there can't be two queens in the same row or same column or diagonal. So how we do that is, so this was the, directly go to the link directly. Okay. So this is an example of where they're talking about backtracking here, right? So you're starting by placing the queen at first position, then you try the second one. It doesn't conflict, all good. But there would be a point where when you're trying to place the fourth queen, there is no, there's no unattacked cell. So that means that's a point where it tells you you need to go back to your last stack frame and you need to change this, right? So they took out this queen from this position, and even then there were no unattacked cells, so they had to even pop out this stack frame, and they had to reprocess that queen's position. So if you look at the code here, so we want to think about, I mean, this is all commented, so you kind of get a pretty clear hint where it's backtracking. But I thought this is a good example to capture. So they are starting with this n queens. You have a board n queens, and you try to place each of them. So you pick a position, you place the queen, and then you try to solve it for rest of the queens. If it's solvable, good. If not, then this is where backtracking is coming in. So you're essentially taking previous queen out from its original position. So you're marking that cell as 0. Does anyone want to add to that, how to think about this? But these were just the initial examples I took to think about backtracking implementation in code. Or if anyone has solved, I believe some of you are pretty active on the lead code practice stuff. So it's how you think about backtracking. We can take more examples, but this is where I got till this point.
Ma'am, shall we take any easy problems and solve apart from this, like permutation of strings, which is super easy?
Yeah, that might be a better one. This is a little. I like this example from concept based, but yeah, this might be a little convoluted. So I haven't tried like other examples yet on backtracking, but I was planning to pick it up next time. But and this is actually where till the point I reached. So I think for today I have this much, but if anyone else wants to cover a problem, we can take that up. Otherwise, we would need to, continue this next week. Sorry, it's not like really full 2 hours, but it's just that I was practicing and there were simpler problems on recursion first.
Yeah, this is perfect, Dippy. I think you're gonna continue that to next session, right? Where we
I think I'll cover this more like somebody suggested about a little more basic on backtracking and then slowly progressing to this, and also dynamic programming stuff. So maybe the maze kind of problems as we build on that. So yeah.
Yeah. I'm just sharing one link of Stanford course in chat window, and that is a good course. It is an old course on C++. Videos are good, but C had a good understanding and explanation of recursion. So if anyone want to watch in more detail, they can go and basically choose that lecture, that talks about recursor.
Great. Yeah. And Bhavesh, maybe you can post that on Slack because I think this link will be lost once.
Yep, I'll do that. I'll do that right away.
Yeah. So yeah, this was pretty much what I had today.
Yeah.
Hey, Dippy, I think this was a good session. Yeah.
Yeah, thanks, Dippy.
Oh, no, thank you. Thanks for
Thank you.
appreciating.
Yeah, it was.
I